Hi everybody, thank you for coming to Wei's seminar. Wei is a fifth-year PhD student working with Ben Kurtman in the Meteorology and Physical Oceanography department. Wei got his undergraduate degree at the University of Nanjing with a major in ocean science, and he's going to be talking today about decadal climate predictability in the global ocean. So Wei's been here for 5 years. His favorite part about Miami is that you can wear shorts and flip-flops, vacation style, to work. And Wei has won the popular vote in Ben's lab group because he always brings delicious candies back from China or wherever he's been traveling to. And Ben always shares them with the group. So Wei's always making the rest of us look bad, but now we get to hear about decadal predictability.
All right, thank you. And thanks for coming today. I mean, it's good to have a small group of people, since you can stop me anytime you want, and we can discuss more about the research. All right? Okay, today I'm going to talk about decadal climate predictability in the global ocean. There's increasing demand for the development of decadal climate prediction systems in order to support decision-making processes in agriculture, algae, water management, as well as extreme climate events in the coming decades. However, compared with seasonal prediction or long-term climate projection, decadal prediction is still at a very early stage of development. Decadal prediction is both initial value and boundary value problem, making decadal prediction much more challenging. So today, I'll focus on 3 major challenges in decadal predictability and prediction. The first challenge is associated with the basic question: to what extent is decadal variability predictable? The limits, sources, and mechanisms of decadal predictability has now been well understood. This red panel shows the very clear observed decadal variations of the global surface temperature, North Atlantic SST, Eastern Tropical Pacific SST, and winter NAO, Sahara rainfall, and accumulated cyclone energy. The thick blue line accounts for 11-year volume, and the black dashed line accounts for external forcing. So, decadal climate variability is driven by both internal dynamics and external forcing, but the relative importance of which is still in debate. And even with prescribed external forcing, there's no consensus on how much of the variability is due to the coupling and how much is due to the noise from the internal dynamics. The second challenge is associated with the signal-to-noise paradox, which may be overlooked in previous studies. So what is the signal-to-noise paradox? Let's look at this figure first. This figure is from Smith et al. 2019, showing an example of the signal-to-noise paradox based on the decadal hindcast of the NL index. The y-axis is the correlation square, x-axis is ensemble size. The blue curve accounts for the correlation between model ensemble mean focus and individual ensemble members. And red curve accounts for the correlation between model ensemble mean focus and the observation, with 5 to 95% confidence interval shaded here. So in the ensemble-based climate predictions, model ensemble mean forecast generally shows higher correlation with observation than with individual ensemble members. This seems to lead to a paradox referred to as the signal-to-noise paradox, that the model makes better prediction for the real world than predicting itself. In other words, the actual prediction scale is higher than the perfect prediction scale. So if the signal-to-noise paradox applies to decadal prediction, for example, our previous estimates of prediction scale based on the ensemble forecast may be an underestimate. And understanding the signal-to-noise paradox may help us identify the potential issues in the model forecast systems in order to provide guidance on future model development and initialization. The third challenge is about the role of ocean dynamics in decadal predictability. As a matter of fact, most simplified models do not simulate decadal variability very well, which is partly due to the low resolution of ocean models that fails to capture the mesoscale ocean features. All the simplified decadal prediction experiments use eddy-parameterized ocean models. High-resolution ocean models are an important component of Sigma 6, but that doesn't include any decadal predictability experiment. Let's look at this panel. This panel shows a snapshot of SST based on cis-example low-resolution, high-resolution simulations and a very high-resolution observations from the satellite data. It's clear that compared with low-resolution cis-example, high-resolution model shows very clear ocean eddies and fronts along the Gulf Stream, which is missing in the low resolution, but is more consistent with the high-resolution observations. So, the first part of my work is about the impact of internal atmospheric noise on decadal climate predictability. It's widely accepted that the noise due to the internal dynamics can significantly impact seasonal into any climate predictability. So how about decadal timescales? And can we increase the decadal predictability by reducing the noise? So based on a simple linear signal plus noise model, where C here is climate variability, S is decadal scale signal, and N is just noise. One may simply argue that when you reduce the noise, you may potentially increase or amplify the signal, and thus you may potentially increase the decadal predictability. But it's rarely the case. To examine the impact of internal atmospheric noise on decadal predictability, here we introduce the intact ensemble coupling strategy. This plot here shows the structure of the intact ensemble coupling strategy. Here we couple multiple realization of the atmospheric component models to a single realization of the ocean model. And only the ensemble mean flexes of the heat, momentum, and moisture are coupled to the ocean. So the basic intent of the intact ensemble is to reduce the internal atmospheric noise at the air-sea interface, which allows us to examine the impact of noise reduction on decadal predictability. Here we perform 2 experiments with cis-SM4, including the control and the intact ensemble simulations. The control experiment is just the standard present-day control experiment, but in the intact ensemble experiment, we use 10 atmosphere coupled to only 1 ocean. To further interpret the intact ensemble simulations, we perform a variance test based on the Hassman hypothesis. We take the Hassman hypothesis as a null hypothesis that the atmosphere is just the white noise and the ocean is a red noise filter. So we provide a very simple form for the coupled system for the control and interactive ensemble simulations. A here is the atmosphere, O is ocean, alpha and beta are coupling strengths. A and P are white noise. And in the eddy simulations, we have M atmosphere coupled to 1 ocean. The eddy control variance ratio is given as follows, which is a function of the coupling strength beta, and the ocean noise divided by the atmospheric noise, and a function of n. This plot shows the function of this I control variance ratio with respect to the ocean noise divided by the atmospheric noise and coupling strength. So it's clear that when the ratio is below 0.1, the null hypothesis works. That means SST variability is totally atmospheric noise forced. And when the ratio is between 0.1 and 1, the SST variability is partly atmospheric noise forced. Either atmospheric noise, ocean noise, or coupled feedbacks can come into play. When the ratio is greater than 1, the null hypothesis fails. Unstable coupled feedbacks or nonlinear dynamics can play a role. This panel shows the distribution of SST decadal predictability based on 2 observational data and CSS sample control and interactive ensemble simulations. The next panel shows the limit of predictability estimated by the nonlinear local Blackstone method. The red panel shows the decadal potential predictability estimated as the ratio of nonlinear low-pass filter variance to the total variance. Let's look at these 2 panels. And in general, these 2 methods give very similar spatial patterns for decadal SST predictability. In the observational estimates, 2 observational datasets show very similar results for the decadal SST predictability. But compared with observational estimates, the CSS sample control simulations present a lower decadal predictability almost everywhere. The bottom panel shows the difference of the IP and control in terms of decadal SST predictability. Let's focus on this bottom panel. You can see both increased and decreased decadal SST predictability in the IE simulations compared with control simulations. So we argue that CSS sample models underestimate decadal SST predictability, and the impact of noise on decadal predictability is not simply a linear problem, but more complex and largely dependent on the regions. This figure A shows the difference of IE control decadal SST predictability. This is the same as the last slide. Figure B shows the IE control variance ratio. You may recall that when the ratio is below 0.1, SST variability is totally atmospheric noise forced. And when the ratio is greater than 0.1, that means other factors like ocean noise, coupled feedbacks, or nonlinear dynamics can come into play. It's quite interesting that there's some kind of close relationship between figure A and figure B. If you take a look at these special patterns of these 2 figures. For example, in figure B, in regions like regions A, C, the ratio is below 0.1. In this region, SST variability is totally atmospheric noise forced. And you go back to figure A, in regions A and C, you can notice a decreased decadal predictability. And also, in figure B, this region like B and D, the ratio is greater than 0.1. And you can see an increased decadal SST predictability in figure A. So let's take a look at this figure. So take a look at these regions A, B, C, D for further analysis. This top panel and bottom panel shows the time series of the SST based on observations and models. And bottom panel shows the autocorrelation functions for these models and observational estimates. Let's focus on these control and IE simulations. The red curve accounts for the IE simulation, and black curve accounts for the control simulations. You may say in regions A and C, the ratio is below 0.1. And also in the autocorrelation plots, you can see a decreased or shorter persistence in the IE simulations compared with control simulations, accompanied by a decreased decadal SST predictability. And in regions B and D, the ratio is greater than 0.1. You can see an increased persistence in IE simulations compared with control, accompanied by an increased decadal predictability. So we argue that the impact of internal atmospheric noise on decadal predictability is dependent on the background regional air-sea coupling and dynamics. In regions where it's totally atmospheric noise forced, reducing the noise decrease decadal SST predictability, and in regions where it's partly atmospheric noise forced, reducing the noise increase the decadal SST predictability. So for our question here, can we increase decadal predictability by reducing the high frequency internal atmospheric noise? Our answer is it depends on the background air-sea coupling and dynamics. So in the second part, I focus on the signal-to-noise paradox in climate predictions. There's an increasing list of examples for the existence of signal-to-noise paradox for different climate models at different timescales. But the mechanisms and even the existence of signal-to-noise paradox have not been well studied. So our first question here is that can we reproduce or explain the signal-to-noise paradox with a simple macromodel framework? And since the signal-to-noise paradox was first identified in seasonal prediction of the annual index, so can we use the macromodel framework to determine the existence of the signal-to-noise paradox in the annual index, as suggested by previous studies? So if we simply consider climate variability as a Markov process and introduce the Markov model framework to represent ensemble forecast and to understand the signal-to-noise paradox. So we build a very simple form for the observation and the free-running model. Here we assume that the future state is depend linearly on the current state and the stochastic error term, where alpha and beta is the Lagrange autocorrelation coefficient, suggesting the persistence of the system. A and P are unpredictable white noise. Then we can make forecast with perfect initial conditions, that is observation. The unique part of this Markov model framework is that we use the observation as the initial condition and keep the key parameters beta and p from the free-running model. This has never been done by previous research. And with different noise realizations, we can make ensemble forecasts. The ensemble mean forecast is given as follows. The ratio of square correlation can indicate the existence of a signal-to-noise paradox, as suggested by Escape and Smith 2018. So, mathematically, we can derive the function for the correlation between model ensemble mean forecast and the observation, and the correlation between model ensemble mean forecast and individual ensemble members. And we derive this ratio of square correlation based on the Markov model framework. When the ratio of square correlation is greater than 1, there's a paradox. So we can derive very simple form for the necessary conditions for the existence of signal-to-noise paradox based on this Markov model framework. And again, this alpha beta can suggest the persistence in the observation and models. And sigma n and sigma p just the noise variance in observation and models respectively. This panel shows an example of the signal-to-noise paradox based on this Markov model framework. The y-axis in figure A is the persistence divided by the noise in observations, and the x-axis is the persistence divided by the noise in models. So we give values to alpha, beta, sigma n, and sigma p that satisfy the necessary conditions for the existence of the signal-to-noise paradox. And you may see this big red point here. The corresponding correlation scale is given in figure B. X-axis is ensemble side. The blue curve is the correlation between model ensemble mean forecast and the individual ensemble members, and red curve is the correlation between models and observations. And it's clear that the correlation between model ensemble mean forecast and observations is greater than the correlation between model ensemble mean forecast and the individual ensemble member forecast. So we successfully reproduce the signal-to-noise paradox based on this Markov model framework. And we further argue that the existence of the signal-to-noise paradox is dependent on the relative amplitude of the persistence and noise variance in models and observations. Here we first apply this Markov model framework to monthly annual index based on 5 observational data and 40 simplified models. The y-axis is monthly annual index, and we plot this time series with 3-year low-pass filter. The black line and the colorful lines accounts for the observational estimates, and a bunch of gray lines correspond to the simplified historical simulations. You may see the observed monthly annual indices show generally consistent variations and are highly correlated. We use different observational data sets to ensure that we thoroughly consider the observed uncertainty of the annual index from different resources or based on different methods. Then, we evaluate the 4 parameters alpha, beta, sigma n, and sigma p in models and observations. The ratio of the persistence and noise variance can indicate the existence of signal-to-noise paradox. So let's look at this figure A first. Figure A shows the autocorrelation functions for the monthly annual index based on the observations and 40 simplified models. The thick black line is the observational estimates, and a bunch of colorful lines are simplified simulations. So it's clear that at that 1 month, the observation shows longer persistence than most of the simplified models. Figure B shows the noise variance for the observations and for the simplified models. The black dot here is observational estimate. So many simplified models have a larger values of noise variance compared with observational estimates. figure C and D can indicate the existence of the signal-to-noise paradox. The y-axis is the y-axis in figure C is a persistent divided by the noise. The x-axis in the observations for the y-axis, and the x-axis is a persistent divided by the noise for the models. So a great number of simplified models have a smaller values of persistent divided by the noise compared with the observational estimates, suggesting the existence of signal-to-noise paradox. And this is much clearer in figure D, shows the ratio of square correlation. When the ratio of square correlation is greater than 1, there is a paradox. And results suggest over 75% of the simplified models have a value of RSC, a ratio of square correlation greater than 1, suggesting the paradox. So we argue that this widespread existence of signal-to-noise paradox in simplified models, and more importantly, this paradox applies to simplified uninitialized historical simulations, suggesting the paradox is not due to the problems in the initialization processes, but instead is a general model problem. In addition to monthly annual index, we're also interested in the winter annual index. So this plot here shows the DGFM annual from 1870 to 2005. The black, red, purple lines are observational estimates, and the gray lines are simplified historical simulations. And again, different observational estimates with different methods of annual index are generally consistent and highly correlated. This panel shows the autocorrelation functions for the winter annual index and the 10-year low-pass filter winter annual index. The thick colored lines and black lines are observational estimates, and the gray lines are simplified historical simulations. So, in general, the observational estimate shows longer persistence than most of the simplified models in both unfiltered and filtered winter annual index. So we argue that persistence in winter annual index is generally underestimated by simplified models, and similar to the monthly annual index, the ratio of square correlation for both unfiltered and filtered winter annual index have a value greater than 1, suggesting the existence of signal-to-noise paradox in winter annual index at different timescales. So, for our question listed here, our answer is yes. We conclude that macro model framework can easily reproduce the signal-to-noise paradox, and is very useful to determine the existence of signal-to-noise paradox in annual index. In the next part, I'll talk more about the signal-to-noise paradox in decadal climate predictability and the impact of ocean model resolution. We are trying to answer the following 3 questions. First, is decadal climate predictability underestimated in simplified models? If so, is it related to the existence of signal-to-noise paradox? And the third question is, will increased ocean model resolution eliminate the signal-to-noise issue? This panel shows decadal SSD predictability based on the observations and simplified models. The decadal SSD predictability is estimated as the ratio of the 5-year low-pass filter variance to the total variance. Here we use 3 observational data, including heavy SST, EI-SST, and copy SST. So figure A is just the mean values of decadal SSD predictability based on these three observational SST datasets. Figure B shows the multimodal mean values of decadal SST predictability based on 30 simplified models. And it's clear that the observational estimate shows higher decadal SST predictability than simplified models, especially in regions like the part of the North Atlantic and part of North Pacific, South Ocean, and the tropical Indian Ocean. Figure C shows the values of decadal SST predictability in 6 regions, including the North Atlantic, North Pacific, Eastern Tropical Pacific, Tropical Atlantic, Tropical Indian Ocean, and South Ocean. And it's much more obvious that the observational estimate shows higher decadal SST predictability than most of the simplified models, except some regions like the North Pacific. But if you see figure A and B, the spatial distributions for the decadal SST predictability in the North Pacific is totally different. So we argue that the decadal SST predictability is generally underestimated in simplified models. This panel is similar to the last slide, but for the atmospheric variable sea level pressure. So figure A is the mean values of decadal SLP predictability based on 3 observational SLP datasets. And figure B is multimodal mean values. And again, the observational estimate shows higher decadal predictability than simplified models. And this is much significant than the decadal SST estimates. And again, in the 6 regions, the observational estimate shows higher number of decadal SLP predictability than almost all the simplified models. So we argue that the decadal SLP predictability is significantly underestimated in simplified models. So for our first question, the answer is yes. Decadal climate predictability is generally underestimated in simplified models. Here we will focus on decadal SST predictability and try to answer the second question. If this underestimate of decadal predictability is related to the signal-to-noise paradox. Figure A here shows the ratio of observation to simplified models in terms of decadal SST predictability. So figure A just the ratio of these 2 plots. Figure A can indicate a rate of underestimate in models. Figure B shows the signal-to-noise paradox at decadal timescales. Here we just plot the chance of existence of the signal-to-noise paradox in 30 simplified models. So for example, in some red color regions, so it's very likely to have a signal-to-noise paradox in these regions, because over 90% of the simplified models present a paradox. If you take a look at these red color regions, which include some eddy-rich regions, including the coastal current, Gulf Stream, and South Ocean, as well as regions like the tropical Indian Ocean and tropical Atlantic region. And in regions like the Eastern Tropical Pacific, the chance of existence for the signal-to-noise paradox is just about as likely as not, because just about 40 to 50% of simplified models present a paradox. It's quite interesting that the red color regions where it's likely to have a signal-to-noise paradox. If you go back to figure A, in these similar regions, the models are underestimating decadal SFT predictability. So they will be somewhat consistent with figure A, except some regions like Eastern Tropical Pacific. Even though there's some uncertainty in the Eastern Tropical Pacific, we can argue that the decadal SFT predictability is likely to be underestimated in models in regions where it's likely to have a signal-to-noise paradox. This panel shows the ratio of square correlation for the 30 simplified models. The ratio of square correlation is estimated based on the Markov model framework. So you may recall that when the ratio of square correlation is greater than 1, there's a paradox. So in regions like the North Atlantic, Tropical Atlantic, and the Southern Ocean, it's very likely to have a signal-to-noise paradox because over 93% of the simplified models have a paradox. In the meanwhile, in regions like the North Pacific and the Eastern Tropical Pacific, only 40 to 50% of simplified models have a paradox. So the chance of existence for the signal-to-noise paradox is just as likely as not. So for the second question, our answer is also yes. We argue that there's a close relationship between the underestimate of decadal SFT predictability and the existence of signal-to-noise paradox at decadal time scales. Even though there's some uncertainty in the Eastern Tropical Pacific, the models is likely to underestimate decadal predictability in regions where it's likely to have a signal-to-noise paradox. The existence of signal-to-noise paradox and the underestimate of decadal SST predictability in eddy-rich regions, such as the crucial current, Gulf Stream, and South Ocean, make us to consider the impact of ocean model resolution. We want to know if an eddy-resolved ocean model can potentially eliminate the signal-to-noise issue. So here we perform 2 experiments with CSSM4, including a low-resolution experiment and high-resolution experiment. In a low-resolution experiment, we perform 500 years of control present-day simulations, and we use IPCC class resolutions with a special resolution of 1 by 1 for the ocean and atmosphere. And we are currently running low-resolution perfect model experiment. And in the high-resolution experiment, we have performed 250 years of control simulations. And different from the low-resolution experiment, we use eddy-resolved ocean models with a special resolution of 0.1 by 0.1. And the atmospheric model resolution remains the same. So here, we first look at this ending as a bias plot. Figure A and B shows the ending as a bias for the simplified models and CSSM4. You may see this considerable model bias in simplified models, including CSSM4, especially in part of the North Atlantic, North Pacific, and the eastern boundary current regions. Figure C shows the difference in high resolution and low resolution in terms of the enemy SST. You may see somewhat opposite signs in figure C compared with figure A and B. So we generally argue that the high-resolution models may potentially improve the enemy SST bias in a low resolution. This two plot shows the decadal SST predictability based on the low resolution and high resolution CSSM4 control simulations. In general, both low resolution and high resolution simulations give very similar spatial patterns. Both show relatively higher decadal predictability in the North Pacific, North Atlantic, and Southern Ocean, and relatively lower decadal predictability in the Eastern Tropical Pacific. Compared with low resolution, there are also many considerable regions showing higher decadal predictability in high resolution simulations. And this is much clearer in Figure A here. Figure A here shows the ratio of the high resolution to low resolution in terms of decadal SST predictability. And again, you can see an increased decadal SST predictability, especially in some eddy-rich regions, including crucial current, Gulf Stream, Southern Ocean, as well as some other regions like the tropical Indian Ocean and tropical Atlantic regions. Figure B here shows the difference of high resolution and low resolution in terms of the persistence divided by the noise. You may recall the necessary conditions for the existence of signal-to-noise paradox based on the Markov model framework. So figure B is just the difference of this beta square divided by sigma p square in high resolution and low resolution. So a positive value in figure B is just the larger value of persistence divided by the noise, suggesting a less chance of existence of the signal-to-noise paradox. And you may see that the crucial current, Gulf Stream, and some eddy-rich region, Southern Ocean, tropical Indian Ocean, tropical Atlantic region have a positive value. So in these regions, there's less chance of existence of signal-to-noise paradox in the high resolution models. And this is consistent with the region of increased decadal SST predictability in the high resolution. So compared with low resolution, high resolution models suggest less chance of existence of signal-to-noise paradox, especially in some eddy-rich regions and tropical Indian Ocean and tropical Atlantic region, where longer decadal predictability is identified. And we expect stronger vertical collection between SST and subsurface ocean leads to this increased SST decadal predictability. So this plot, we take a look at this North Atlantic region. We examine the correlation between SST and the upper 500 meter vertical average ocean temperature. And we find that there's stronger subsurface vertical collection along Gulf Stream in this area in the high resolution compared with low resolution, supporting our argument that strong vertical collection may contribute to this increased decadal SST predictability in these regions. So for the last question, we argue that an eddy-resolved ocean models may at least partially eliminate the signal-to-noise issue. So to summarize, in the first part, we introduced the interactive ensemble coupling strategy to CSSM4, and we argue that the impact of internal atmospheric noise on decadal predictability is dependent on the regional air-sea coupling and dynamics. In part 2, a simple micromodel framework can easily reproduce a signal-to-noise paradox, and the existence of the paradox is dependent on the relative amplitude of the persistence and noise balance in models and observations. And there's widespread existence of signal-to-noise paradox in simplified models, and the paradox applies to simplified uninitialized historical simulations, suggesting the paradox is not due to the problem in the initialization processes, but instead is a general model problem. In part 3, we find decadal climate predictability is generally underestimated in simplified models, which is closely related to the existence of the signal-to-noise paradox. And comparison of CSSM for low-resolution and high-resolution simulations suggests that increased optimal resolution may potentially eliminate the signal-to-noise issue. It's a reference. Thank you. Any questions? Yes.
That was really interesting. Thank you. Nice work. So, based on your maps of the decadal predictability, I don't have a whole lot of background on sources of predictability on decadal timescales. So, ENSO is just noise on a decadal timescale. Is that what those maps are telling me?
Because we take a decadal scale low-pass filter to this data, so the ENSO signal just partly almost removed.
Okay.
That's why decadal predictability averages. Yeah.
So if I summarize the paradox, it looked like, just at the highest level, 30,000 foot level, it looks like at least at longer time scales, the lack of persistence is the big issue. The models lack persistence.
Yes.
Is that a fair conclusion, or am I just not, or we just not have, you just haven't really looked at the details of the noise? Is the noise really playing a role, or is it just the persistence that really is the problem?
I think I tested the decadal scale signal-to-noise paradox in this plot. Yes, this one. So for this plot, I didn't include the noise. It's just the persistence.
It's just the persistence.
Because I also plot the map included the noise. The results totally different. But if you just include the persistence, the results is more consistent with this plot.
So that plot is more like the
Persistence.
persistence problem is why we're underestimating.
Yes.
Not the, which is actually, I guess, is a comforting result, because if you're getting a relatively low, you're not getting a signal to noise paradox, but your persistence is weak, that means your noise also has to be weak. So you're getting a lack of a paradox for the wrong reason.
Yes.
Right? So that would be a bad thing. The other thing is that, if I can not watch the vertical connectivity, I don't know if it's the projector or what, but it's hard to see the difference. Just so you know.
Yeah, it's kind of hard.
It's kind of hard to see. I don't know if it's the projector.
This value is like 0.4,
Yeah.
but this average value is like 0.6.
You might need to take a difference or something to highlight.
Yes.
Any other questions?
You looked at the vertical connectivity in those other regions that you highlighted.
Yes.
It's the same thing.
Yeah. So I just focus on this nonsense map to see it clearly.
All right, let's think away.
Thank you.